Have you ever stared up at the night sky and felt that strange, almost dizzying sensation, the realization that every star you see is just a tiny fraction of something unimaginably vast? The universe stretches far beyond what our eyes can perceive, beyond even the most powerful telescopes. Out there, at the very edge of everything we can observe, lies a boundary not just of space, but of human understanding. Beyond it, the cosmos becomes a mystery wrapped in shadows. What lies past that final frontier? Is there an end to the universe, or does it stretch on forever, dissolving into something even more extraordinary? We've spent centuries mapping the heavens, from the first astronomers tracing constellations to the Hubble telescope capturing galaxies billions of light years away. Yet for all our progress, the observable universe has a limit, an edge shaped by the speed of light and the age of the cosmos. Beyond that edge, light hasn't had enough time to reach us. It's a horizon we can't cross, a border that keeps the deepest secrets of existence just out of reach. But here's the thrilling part: the unknown doesn't stop us from asking, from imagining, from pushing our theories to the brink. What if the universe isn't alone? What if it's just one bubble in an infinite cosmic foam, or part of a multiverse where the laws of physics rewrite themselves endlessly? This journey isn't just about distant galaxies or abstract science, it's about the human spirit. We're the only species we know of that looks up and wonders what's beyond the beyond. That curiosity has taken us from cave paintings to moon landings, and now to the edge of reality itself. In this video, we'll explore the wildest ideas in cosmology, from theories about the shape of the universe to the mind-bending possibility of worlds beyond our own. We'll meet the scientists daring to ask these questions and the experiments that might one day reveal answers. So come with me to the farthest reaches of imagination, where the known universe ends and the real adventure begins. The observable universe is our cosmic backyard, the portion of reality we can actually see and study. Picture it like standing in the middle of an endless forest at night, holding a lantern. The light only reaches so far, revealing trees in a small circle around you. Everything beyond that, swallowed by darkness. For us, that lantern's glow stretches 93 billion light years across, a sphere nearly unfathomable in scale. But here's the catch: that number isn't just about distance, it's a time capsule. Because the universe is 13.8 billion years old, and light can only travel so fast, we're forever trapped inside a bubble where the oldest light has finally reached us after an epic journey across space and time. This cosmic horizon isn't a physical barrier like a wall at the edge of existence. It's more like a curtain drawn by the laws of physics themselves. Beyond it, galaxies might be rushing away so fast that their light will never catch up to us, stretched thin by the universe's relentless expansion. We call this the Hubble volume, named after the telescope that revealed our cosmos is growing like an inflating balloon. Every second, that horizon creeps outward as new light arrives, but the universe's expansion fights back, pushing some regions of space permanently out of view. What's wild is that the observable universe keeps surprising us. Early astronomers thought the Milky Way was everything until Edwin Hubble proved galaxies existed beyond it. Today, we know there are likely 2 trillion galaxies in our observable bubble, each with billions of stars. Yet all of that might be less than a speck in the full universe, if full even means anything when space could stretch on infinitely. The paradox: we'll never know for sure. The cosmos plays this cruel game with us. The more we learn, the more we realize how much is hidden. But that's also what makes it thrilling. Every photon that reaches us from the edge is a messenger from the dawn of time, whispering secrets about how everything began. That faint glow you see between the stars, it's not just empty darkness. It's the cosmic microwave background, the oldest light in the universe. A whisper from a time before galaxies, before stars, even before atoms as we know them. Picture this: 13.8 billion years ago, the universe was a searing hot soup of particles, so dense and energetic that light couldn't travel more than a fraction of an inch before crashing into something else. Then, around 380,000 years after the Big Bang, everything changed. The cosmos cooled just enough for atoms to form, and suddenly, light could race freely across space for the first time. That flash of liberation is what we're still detecting today, a fossilized echo stretched into microwaves by the universe's expansion. Think of the CMB like finding a baby picture of the cosmos. It captures the universe at a pivotal moment when it transitioned from a chaotic fireball to something more recognizable. The patterns we see in this light, those subtle variations in temperature, are the seeds of everything that came after. The slightly denser patches became galaxies, the cooler spots grew into vast cosmic voids. This is where structure began, written in heat and radiation. And here's the mind-bending part. When we map the CMB, we're not just looking at distant space, we're peering back in time, seeing the universe as it was before Earth, before the Sun, before anything we'd call familiar even existed. But the CMB isn't just a relic, it's a Rosetta Stone for cosmologists. By studying its subtle imperfections, scientists have pieced together the universe's composition, its age, even its ultimate fate. It's how we know dark energy and dark matter dominate our cosmos, invisible forces shaping reality on scales we can barely comprehend. And it's not static. The Planck satellite and other instruments have mapped it with stunning precision, revealing anomalies that still puzzle researchers. Why, for instance, is one half of the sky slightly warmer than the other? Could it be a clue to something beyond our observable bubble? The cosmic microwave background is more than light, it's a boundary. It marks the furthest back we can see, not because the universe didn't exist before, but because earlier times were opaque, a fog of plasma no telescope can pierce. Beyond this wall of light lies the Big Bang itself, hidden from view. Yet even here, at the edge of observation, the CMB hints at deeper mysteries. Some theories suggest its patterns could reveal echoes of a universe before the Big Bang, or even the presence of other universes in a vast multiverse. It's a humbling thought. The afterglow of creation, still carrying secrets we're just beginning to decode. The universe isn't just expanding, it's accelerating, racing outward faster with every passing second. Picture a balloon with dots drawn on its surface. As you blow it up, the dots drift apart, not because they're moving across the balloon, but because the fabric of the balloon itself is stretching. That's exactly how space behaves. Galaxies aren't speeding through space like cars on a highway. They're being carried apart by the stretching of space-time itself. And here's where things get stranger. The expansion isn't slowing down. It's speeding up, as if some invisible force is blowing harder on that cosmic balloon. We call this force dark energy, and it's one of the most perplexing mysteries in modern cosmology. Unlike gravity, which pulls things together, dark energy pushes space apart, a kind of anti-gravity woven into the fabric of reality. The effect is subtle on small scales. Within our galaxy, gravity keeps stars tightly bound, and even nearby galaxies like Andromeda are close enough that gravity overrides the expansion. But venture farther out and dark energy dominates. Galaxies billions of light years away are being swept outward so fast that their light will never reach us. They've crossed our cosmic event horizon, disappearing from view like ships vanishing over the edge of the ocean. This acceleration has a startling implication. The observable universe is actually shrinking over time. Not in size, the bubble still grows as new light arrives, but in terms of what we'll ever be able to see. Right now, we can observe galaxies about 33 billion light-years away, but with space stretching faster and faster, future astronomers might see far less. Billions of years from now, distant galaxies will have receded so far that only our local cluster will remain visible. The rest will fade into darkness, their light stretched into undetectable infrared whispers or lost entirely. The universe won't just feel empty, it will become empty, at least to any observer inside it. Why does this happen? Think of dark energy as a property of empty space itself. The more space expands, the more dark energy there is, creating a runaway effect. Some theories suggest it's tied to quantum fluctuations, particles popping in and out of existence even in a vacuum. Others propose it's evidence of extra dimensions or a sign that our understanding of gravity is incomplete. What's certain is that dark energy makes up about 70% of the universe's total energy, yet we've never directly detected it. It's hiding in plain sight, shaping the fate of everything while leaving no fingerprints behind. The balloon analogy helps, but it's not perfect. Unlike a balloon, the universe might have no center and no edge. Every galaxy sees itself as the middle of the observable universe, surrounded by its own sphere of visibility. And while the balloon's surface is two-dimensional, space is three-dimensional, stretching in directions we can't easily visualize. That's why cosmologists use mathematics to describe expansion, tracing how wavelengths of light stretch into redder colors as space carries galaxies apart, a phenomenon called redshift. The farther away a galaxy is, the faster it appears to recede, not because it's moving, but because more space is expanding between us. This relentless expansion doesn't just hide galaxies, it erases them from our future. Take a galaxy right at the edge of our observable horizon today. Its light, emitted billions of years ago, is just reaching us now. But because space has stretched during that light's journey, the galaxy itself is now much farther away than when it sent that light. By the time we see it, it's already unreachable, receding faster than light speed. It's like trying to catch a train that's accelerating away the moment you spot it. What's beyond that horizon, we'll never know. The universe could be infinite, with galaxies stretching forever, or it could curve back on itself like the surface of a sphere. Some theories suggest other bubble universes, each with different physical laws, floating in a vast multiverse. But for us, the observable universe is all we'll ever have, a finite island in an ocean of uncertainty, shrinking slowly as the tides of dark energy pull it away. Imagine a future astronomer billions of years from now pointing their telescope into the night sky. Where we see a tapestry of distant galaxies, they'll find only darkness. Not because the stars have burned out, but because the universe has stretched itself thin, carrying entire galaxies beyond the reach of sight. This isn't science fiction, it's the inevitable consequence of dark energy's relentless push. Every second, millions of galaxies cross a point of no return, their light stretched too far, their signals too faint to ever reach us again. It's as if the cosmos is slowly erasing itself from our view, leaving behind a void where there was once a crowded sky. This phenomenon has a name, the lonely universe hypothesis. As expansion accelerates, galaxies outside our local group, those gravitationally bound to the Milky Way, will one day vanish completely. The observable universe, already a tiny fraction of the whole, will shrink further, isolating us in an island of stars. Future civilizations might gaze upward and see nothing beyond their own galaxy, unaware that trillions of others ever existed. The cosmic microwave background itself will fade, its signals redshifted into silence. The universe won't just feel empty, it will become empty, at least to any observer within it. What's haunting is how permanent this loss will be. Light from those fleeing galaxies isn't just delayed, it's severed. Space itself is expanding faster than light can traverse it, creating regions we can never interact with, no matter how advanced our technology becomes. It's like being stranded on a shrinking raft, watching the ocean around you evaporate. And here's the twist, this isn't just a distant future problem. It's already happening. Right now, galaxies at the very edge of our observable horizon are slipping away, their light growing dimmer with each passing century. The lonely universe scenario forces us to confront a profound irony. The same expansion that made life possible, by cooling the early cosmos and allowing matter to clump into galaxies, will eventually render most of those galaxies invisible. Future astronomers might never know the universe was once lush with stars, or that their own galaxy was just one among countless others. They could develop entire models of cosmology based on a single data point, their own isolated corner of existence. Yet this isolation might hold clues to deeper truths. Some theorists suggest that the lonely universe could be evidence of a multiverse. If other bubble universes exist beyond our horizon, their gravity might subtly warp the fabric of space-time in ways we could detect. Others argue that the accelerating expansion could hint at undiscovered physics, a flaw in Einstein's equations, or a new force waiting to be uncovered. Even in its emptiness, the future cosmos might still whisper secrets about its origins. For now, we're privileged to live in a golden age of cosmic observation. We can still see the universe in its adolescence, teeming with galaxies, their light a fossil record of a more connected era, but the clock is ticking. Every galaxy that vanishes takes with it a piece of the cosmic story, a chapter we're only beginning to read. The question isn't just what we'll lose, it's what we can learn before the curtain falls. We're used to thinking of the universe's edge as a distant place, but its real boundary might lie far closer in the first sliver of time itself. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, but what about the era before that? Here, physics places a brick wall in front of our curiosity. To peer further back, we'd need to see light from that primordial fireball, but the early universe was so dense that photons couldn't travel freely. They were trapped in a plasma thicker than molten lead, constantly colliding with electrons. This opaque curtain only lifted when atoms formed during recombination, releasing the light we now detect as the CMB. But there's an even more fundamental barrier, the Planck time. This is the universe's smallest possible stopwatch tick, 10 to the minus 43 seconds after the Big Bang. At this scale, space and time cease to behave as we know them. Gravity becomes as chaotic as the quantum foam, with tiny wormholes flickering in and out of existence. Probing this era would require particles with so much energy they'd collapse into black holes, shredding any information they carried. It's like trying to read a book where the pages dissolve the moment you touch them. Quantum mechanics adds another layer of mystery. At these extreme scales, fluctuations in the vacuum of space become so violent that they might scramble any data from the universe's birth. Imagine recording the first cry of a newborn, only to have the tape erased by static. Some theories suggest this cosmic noise isn't just interference, it's a fundamental limit. The very act of observing those first moments could disrupt them, leaving us with only faint echoes in the CMB's patterns. Then there's inflation, the universe's dramatic growth spurt. In less than a trillionth of a second, space expanded faster than light itself, stretching quantum ripples into the seeds of galaxies. But this process also stretched any earlier information beyond recognition, like blowing up a photograph until the pixels blur into nothingness. What existed before inflation? Was there a previous universe or a quantum bounce from a prior contraction? These questions might never have answers because inflation didn't just reshape space, it erased its own fingerprints. The irony is crushing. The universe's earliest moments set the stage for everything we see today, yet they're locked away by the very physics that made them possible. We're left studying shadows on the cave wall, reconstructing the fire from its glow. But perhaps that's the point. The cosmos teases us with glimpses, reminding us that some mysteries aren't meant to be solved. They're meant to keep us reaching. The idea of a multiverse isn't just science fiction, it's a serious scientific hypothesis, born from the edges of cosmology and quantum physics. Picture our universe as just one page in an infinite book, where every page holds a different set of physical laws, a different arrangement of stars, even different versions of reality itself. This isn't fantasy, it's a natural extension of the math behind inflation, string theory, and quantum mechanics. And while we can't see these other universes, their existence might solve some of the deepest puzzles about our own. Take inflationary bubble universes first. According to this theory, the rapid expansion of space during the Big Bang wasn't a one-time event. It's still happening in distant regions, creating pockets of spacetime that pinch off into separate universes. Imagine a pot of water boiling endlessly, with each bubble rising to the surface representing a new cosmos, each with its own unique physics. Some might collapse instantly, others could harbor life. Our universe is just one accidental success in an endless froth of possibilities. The eerie part, these bubbles could be drifting right past us, forever out of reach, their light never crossing the gulf between their space and ours. String theory takes this even further. It suggests that what we call the universe might be a three-dimensional brane, floating in a higher dimensional space, like a sheet of paper suspended in a vast room. Other branes, other universes, could be hovering mere millimeters away in these extra dimensions, utterly invisible because all known forces, including light, are trapped on our brane. Every now and then, these parallel sheets might collide, triggering cataclysms like the Big Bang itself. It's a staggering thought. The birth of our cosmos could have been just a ripple in a far larger cosmic ocean. Then there's the quantum multiverse, where every decision spawns a new reality. In this view, the universe isn't a single timeline but a branching tree, with every possible outcome playing out somewhere. You flip a coin, and in one universe it lands heads, in another tails. This isn't just philosophy, it's a mathematical consequence of how quantum wave functions behave. Particles exist in superpositions until observed, and some interpretations argue that each observation splits reality into parallel threads, the catch. These alternate worlds are forever sealed off, their existence inferred only through equations. The wildest part is how these theories might leave fingerprints in our own universe. If another bubble universe once brushed against ours, the collision could have left scars in the cosmic microwave background, oddly cold spots or ripples in spacetime. Some researchers claim to have spotted these anomalies, though the evidence remains controversial. Others suggest dark energy's mysterious strength could be a side effect of neighboring universes tugging on ours through hidden dimensions. Even the universe's unsettlingly perfect fine-tuning for life might make sense if there are infinite versions, each rolling the dice on different physical constants. We just happen to live in the one where the numbers worked out. Critics argue the multiverse is untestable, more metaphysics than science. But proponents counter that it's the opposite, a natural prediction of well-established theories, from inflation to string theory. The real challenge isn't whether other universes exist, but whether we'll ever find a way to glimpse them. For now, they linger at the edge of imagination, a haunting reminder that our cosmic horizon might not be the final frontier, just the first. Eternal inflation takes the idea of an expanding universe and pushes it to the limit, suggesting that the Big Bang wasn't a one-time event, but just the beginning of an endless cosmic cascade. Picture a runaway fireworks display where each explosion spawns a dozen more, ad infinitum. That's how space might behave on the grandest scales, with regions of spacetime continuously stretching and pinching off into separate universes, each with its own unique physics. This isn't just theoretical speculation. It's a direct consequence of quantum fluctuations meeting gravity's pull during the universe's earliest moments. Alan Guth, the physicist who first proposed cosmic inflation, realized something startling. Under the right conditions, inflation wouldn't just stop after creating our universe. Instead, it could become self-sustaining, a process where quantum effects keep certain regions expanding exponentially forever. In these zones, space stretches so fast that pockets of stability, like our own universe, form as bubbles within the chaos. These pocket universes drift apart, their boundaries receding faster than light, isolating them from one another completely. It's like boiling water where steam bubbles rise and pop, except here, the bubbles become entire realities, each cooling into its own cosmos with potentially different fundamental forces, particle masses, or even dimensions of space. What's wild is how drastically these universes could differ. In one, gravity might be 10 times stronger, crushing stars into black holes before life could emerge. In another, electromagnetism could be too weak to bind atoms, leaving nothing but a sea of loose particles. Our universe's delicate balance, where constants like the strength of nuclear forces or the mass of electrons allow for galaxies, planets, and life, might be a rare accident in an infinite multiverse where most bubbles are sterile or short-lived. This idea, called the anthropic principle, suggests we only observe a universe suited to us because we couldn't exist in the others. Evidence for eternal inflation is indirect but tantalizing. The cosmic microwave background's slight irregularities match predictions of quantum fluctuations stretched by inflation, and models show these fluctuations could naturally lead to eternal expansion. Some theorists even propose that collisions between adjacent bubble universes might leave imprints in the CMB cosmic bruises from run-ins with other realities. While no such marks have been confirmed, the search continues, with telescopes scanning the sky for anomalies that might betray our universe's crowded neighborhood. The implications are humbling. If eternal inflation is real, then every possible universe exists somewhere in the multiverse's foam. Some might contain stars made of pure dark matter, others could have time flowing backward or laws of physics we can't begin to comprehend. And just as our bubble inflated from a speck smaller than an atom, countless others are doing the same right now, unreachable and unseen. The cosmos becomes less a single entity and more a fractal of possibilities, forever growing, forever dividing, a cosmic kaleidoscope where we've caught just one glittering fragment. String theory reshapes our cosmic perspective by suggesting that the universe isn't just three-dimensional. It's a symphony of hidden dimensions vibrating beneath reality's surface. Imagine plucking a guitar string. The note it plays depends on how it vibrates. Now replace that string with something unimaginably tiny, a one-dimensional filament of energy, and you've got the basic idea. These strings don't just produce musical notes, they give rise to particles, forces, even the fabric of space-time itself. But here's the catch: for the math to work, these strings need room to dance, not just the 3 dimensions we know, but 6 or 7 more, curled up so small we'd never notice them. This is where the concept of braneworlds enters the picture. Think of our universe as a 3-dimensional sheet, a brain, floating in a higher dimensional space called the bulk. Like a piece of paper suspended in air, our brain could be one of many, each hosting its own universe with unique physics. Gravity, unlike other forces, might leak into the bulk, explaining why it's so weak compared to electromagnetism or nuclear forces. This leakage could also create mind-bending possibilities. Parallel brains drifting millimeters away in a dimension we can't perceive, their presence only detectable through subtle gravitational tugs or cosmic anomalies. Some models even suggest the Big Bang was a collision between 2 brains, a cosmic car crash in higher dimensional space. The energy of that impact could have sparked our universe's birth, leaving ripples in the cosmic microwave background as evidence. Other theories propose that black holes might be bridges to neighboring brains, their singularities punching holes through space-time like needles piercing fabric. While these ideas sound like science fiction, they emerge from equations attempting to unify quantum mechanics and gravity, a puzzle that stumped physicists for a century. The wildest implication: if extra dimensions exist, there could be entire universes separated from us by less than the width of an atom, yet entirely unreachable. Light and matter might be trapped on their respective brains, making adjacent realities as invisible as ghosts, but occasionally, gravity's subtle whispers could hint at their presence. Some experiments hunt for these clues by probing microscopic distances, searching for deviations in Newton's famous inverse square law. If gravity weakens faster at incredibly small scales, it might mean we're sensing its lines of force leaking into unseen dimensions. Critics argue that string theory's elegance comes at a cost: testability. Without direct evidence of extra dimensions or vibrating strings, the theory remains a beautiful hypothesis. Yet its mathematical consistency keeps it alive, offering potential solutions to cosmology's biggest riddles, from dark energy's origin to the universe's perplexing fine-tuning. Whether it's the final answer or a stepping stone to something deeper, string theory forces us to confront a humbling truth. Reality might be far stranger and far richer than our three-dimensional intuition allows. What if everything you see, the stars, your hands, even the screen in front of you, is nothing more than an illusion, a cosmic mirage projected from the edge of reality? This isn't the plot of a sci-fi movie, it's the holographic principle, one of the most radical ideas in modern physics. At its core, it suggests our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundary, like a movie playing on an immeasurably vast screen. The pixels of this cosmic film, tiny, vibrating bits of information, each holding the blueprint for everything inside the universe. This bizarre concept first emerged from an unexpected place: black hole physics. When matter falls into a black hole, it doesn't just vanish. Its information gets scrambled and smeared across the event horizon, the point of no return. Physicist Jacob Bekenstein calculated that the entropy, the disorder of a black hole, is proportional to the area of its event horizon, not the volume inside it. That's like saying the contents of a box are determined by the label on its surface, not the space within. This discovery hinted that the universe might store data in the same way, encoding the full complexity of three dimensions onto a two-dimensional boundary. Think of it like a credit card hologram, a flat surface that creates the illusion of depth when light hits it. The holographic principle takes this idea to cosmic extremes, proposing that the entire universe could be a projection from an unimaginably distant boundary we'll never see. Even stranger, it suggests that space itself isn't fundamental but emerges from quantum interactions on this lower dimensional surface, like the 3D world of a video game arising from lines of code on a flat disk. The implications scramble our intuition. If the holographic principle is true, then every particle, every force, even time itself might be secondary ephemeral shadows cast by interactions happening elsewhere. This would mean that the universe has a hard limit to how much information it can contain, just as a hard drive has finite storage. The math suggests that the maximum information in any region of space doesn't depend on its volume, but on its surface area, an idea that overturns centuries of assumptions about reality's structure. But how could we ever test such an outlandish idea? Surprisingly, there are glimmers of hope. Some physicists propose that subtle quantum fluctuations in space-time, tiny fuzziness at the smallest scales, might betray the universe's true two-dimensional origins. Others are searching for distortions in the cosmic microwave background or anomalies in particle collisions that could hint at the underlying code. It's like looking for pixelation in what we thought was smooth reality. The holographic principle doesn't just challenge our understanding of space, it blurs the line between information and existence. If the universe is a projection, then what's projecting it? Could there be a deeper layer of reality where the real universe resides? Or is this just how nature works, with higher dimensions folding into lower ones like a cosmic origami trick? For now, this idea remains at the frontier of physics, a tantalizing hint that the ultimate nature of reality might be stranger and simpler than we ever imagined. What if the universe has no beginning and no end, just an endless cycle of rebirth, where each Big Bang emerges from the ashes of a previous cosmos? That's the extraordinary claim of Roger Penrose's conformal cyclic cosmology, a theory that rewrites the cosmic story as an infinite loop. Picture this, our universe isn't the first and won't be the last. Instead, trillions of years from now, when all matter has decayed into radiation and black holes have evaporated, the universe will stretch into an eerily smooth, empty state. But here's the twist. That vast, featureless expanse could become the seed for a new Big Bang, resetting the cosmic clock. Penrose's genius lies in the math. He realized that at the far end of time, when particles are so spread out that distances lose meaning, the universe's geometry could forget its scale. Space would become mathematically identical to the ultra-dense state of the Big Bang. It's like zooming in on a fractal until the pattern repeats. The end looks just like the beginning. Under these conditions, the dying universe could seamlessly transform into a new one, with no singularity or boundary between them, just an infinite series of cosmic eons. The wildest part, Penrose claims to have found evidence in the cosmic microwave background. He and collaborators identified strange, circular patterns in the CMB's temperature fluctuations, regions where the temperature variations are suspiciously symmetric. These Hawking points, named after Stephen Hawking, could be imprints of supermassive black holes from the previous eon, their final bursts of radiation etched into the fabric of the new universe like cosmic scars. Critics argue these patterns could be statistical flukes, but if confirmed, they'd be the first tangible hint of a universe before our own. This idea flips conventional cosmology on its head. Instead of a one-time Big Bang followed by eternal expansion, time becomes a wheel turning endlessly. Each cycle inherits subtle traces of the last, like ripples passing through a pond. Stars, galaxies, and life may arise anew, but the underlying laws of physics could shift slightly with each rebirth, a cosmic game of telephone where the rules evolve across cycles. The implications are staggering. If Penrose is right, the universe isn't just recycling matter, it's recycling information. Black holes, often seen as cosmic dead ends, might instead be messengers between eons encoding data in the CMB. And the nothingness we fear at the end of time, it's just the prelude to another dawn. For all its controversy, conformal cyclic cosmology offers something profound. A vision of eternity where even the heat death of the universe isn't the end, but a pause before the next cosmic breath. At the very edge of reality, where the universe stretches thin and time loses its grip, something extraordinary stirs in the void. Empty space isn't truly empty, it's a seething quantum sea, alive with particles blinking in and out of existence like fireflies in the dark. These are virtual particles born from the universe's zero-point energy, a kind of baseline hum of reality that never quiets. For fleeting moments, pairs of particles and antiparticles emerge, borrow energy from the vacuum, then annihilate before physics can object. But at the cosmic horizon, where space-time warps and stretches to its limits, these quantum fluctuations might do more than flicker. They could ignite entire new universes. Picture the quantum foam, a turbulent layer at the smallest scales of space-time, where the fabric of reality churns like ocean spray. Here, wormholes and tiny bubbles of space-time form and dissolve in less than a Planck second. Most collapse instantly, but under the extreme conditions at the universe's edge, where gravity and quantum forces dance on a knife's edge, some bubbles might inflate instead of popping. Like a single spark caught in an updraft, a quantum fluctuation could balloon into a full-fledged cosmos, pinching off from its parent universe to grow independently. It's as if the vacuum itself is fertile, spawning pocket realities in its endless expansion. This process hinges on inflation, the same mechanism that supercharged our universe's growth after the Big Bang. In the quantum foam, a random fluctuation might trigger a patch of spacetime to inflate exponentially, its energy driving an unstoppable expansion. As it stretches, it cools, allowing matter and forces to condense into new laws of physics, perhaps ones wildly different from our own. Some theories suggest this is how our universe began, as a quantum blip in some greater multiverse, a bubble that got lucky. And if it happened once, it could be happening endlessly at the boundaries of existence, a cosmic chain reaction where universes birth more universes. The strangest part, these newborn universes might be forever hidden from us. The space between them stretches faster than light can cross it, leaving no bridge for observation or travel. They're like ships sailing into separate dimensions, each carrying its own version of reality. Yet their existence could solve one of cosmology's deepest puzzles: why our universe seems so finely tuned for life. If infinite universes sprout with random physical constants, some will inevitably land in the sweet spot where stars, planets, and consciousness can arise. We're not in a special universe, just one of countless possibilities where the dice rolled in life's favor. Evidence for this audacious idea is elusive but not impossible to imagine. Some models predict that colliding bubble universes might leave imprints in the cosmic microwave background, circular patterns or temperature anomalies where our universe brushed against another. Others suggest that gravitational waves from ancient quantum events could ripple through space-time, detectable by future observatories. Even dark energy, the mysterious force accelerating cosmic expansion, might be a relic of this eternal birthing process, a pressure leftover from our universe's own quantum origins. What's humbling is the scale of it all. The same quantum jitters that create fleeting particles in a lab might, under the right conditions, craft entire cosmoses. It turns the edge of the observable universe from a barren frontier into a creative furnace, where physics weaves new realities from the fabric of nothingness. And if that's true, then our universe isn't the main event. It's just one note in an infinite symphony, playing in harmony with others we'll never see. Deep in the cosmos, something strange tugs at the fabric of reality, not just expanding it, but pulling it in a direction that defies logic. Astronomers call it dark flow, a mysterious current sweeping entire galaxy clusters toward the universe's edge at blinding speeds. Imagine dropping dye into a river and watching it stream not downstream but sideways, as if some unseen whirlpool lurked beyond the horizon. That's the enigma scientists face: hundreds of massive galaxy clusters, each weighing 1,000 Milky Ways, drifting uniformly toward a point in space we can't see, as though drawn by a gravitational hand from beyond our cosmic bubble. This discovery came from studying the cosmic microwave background's subtle distortions. As galaxy clusters move through space, their hot gas scatters CMB photons, leaving a faint imprint called the kinematic Sunyaev-Zeldovich effect. When researchers mapped these imprints, they found clusters hurtling at over 2 million miles per hour toward the same patch of sky, far faster than the universe's expansion should allow. The oddest part, this motion points nowhere special, just an unremarkable void between constellations Centaurus and Vela. No known supercluster or concentration of matter explains the pull. It's as if the universe has a hidden slope, tilting everything toward an unseen abyss. One radical explanation suggests the dark flow could be the gravitational tug of another universe. Picture our cosmos as a soap bubble floating in a froth of others. If a neighboring bubble brushed against ours long ago, its mass might still exert a pull on our galaxy clusters, like a magnet dragging iron filings through paper. This idea ties into multiverse theories, where inflation spawns countless bubble universes, some close enough to interact. Critics argue it's untestable, an exotic answer for lack of better options. But supporters counter that precise measurements of distant clusters could reveal whether the flow strengthens with distance, a hallmark of influence from beyond our horizon. Alternatively, the culprit might lurk within our own universe's shadowy architecture. Dark energy, the force accelerating cosmic expansion, isn't perfectly uniform. Could uneven dark energy create currents in spacetime, like wind-pushing sailboats? Or perhaps our understanding of gravity breaks down at cosmic scales, requiring revisions to Einstein's equations. Some modified gravity theories, like MUND, attempt to explain galactic rotations without dark matter. Could they also account for dark flow? The challenge is that no tweak yet explains both the flow's scale and its eerie alignment. Then there's the unsettling possibility that dark flow doesn't exist at all. Skeptics point to measurement uncertainties, arguing that statistical noise or unaccounted gas movements might mimic the effect. New data from telescopes like Euclid and the James Webb could settle the debate, either confirming the flow's persistence or exposing it as a cosmic mirage. But if it's real, the implications rewrite our place in the cosmos. Not only is the universe expanding, it might also be sliding, pulled toward something vast and invisible, a reminder that even the edge of the observable isn't the end of the story. The dark flow mystery exposes how little we grasp about the forces shaping reality. Whether it's evidence of a multiverse, flaws in our physics, or just a measurement glitch, one thing's certain: the universe keeps surprising us. Every time we think we've mapped the limits of the known, the cosmos whispers, or in this case, tugs us toward the next frontier. Hidden in the depths of space, a gravitational giant lurks just beyond our sight, the Great Attractor. This colossal mystery, weighing in at a staggering quadrillion suns, tugs our entire galactic neighborhood toward it with irresistible force. Picture yourself floating in a vast river, carried by a current you can't see or fully comprehend. That's exactly what's happening to the Milky Way and its neighboring galaxies, all streaming toward a gravitational epicenter over 200 million light-years away in the constellation Norma. What makes this cosmic phenomenon so puzzling is its location directly behind the dense star fields of our own galaxy's disk, an area astronomers call the zone of avoidance. The Milky Way's bright core and thick dust clouds obscure nearly 20% of the sky, creating a blind spot that masks the Great Attractor's true nature. It's like trying to study a mountain peak while standing in a fog bank. Early X-ray telescopes could barely penetrate this region, leaving scientists to piece together clues from the motion of galaxies caught in its pull. But here's where the plot thickens. The Great Attractor alone doesn't account for the full scale of our supercluster's movement. There's something even bigger at play: the Shapley supercluster, a behemoth structure 8 times more massive, lying another 600 million light-years beyond the Great Attractor. This sprawling metropolis of galaxies, containing tens of thousands of members, might be the true mastermind behind the dark flow dragging us through space. Think of the Great Attractor as a way station on a cosmic highway, with Shapley as the ultimate destination. The real intrigue lies in what these structures reveal about the universe's hidden architecture. Normal matter, the stars and galaxies we can see, accounts for less than 5% of the Great Attractor's gravitational muscle. The rest comes from dark matter's invisible scaffolding, woven through space in vast sheets and filaments. These form the cosmic web, a network of matter that channels galaxies into dense knots like water flowing into drain pipes. Our local group, the Virgo cluster, and countless others are all part of this grand choreography, dancing to gravity's tune on scales that boggle the mind. Some theorists propose an even wilder possibility. The Great Attractor might be a signpost pointing to structures beyond our observable horizon. Just as sailors once used the moon's pull to deduce unseen continents, astronomers now study galaxy flows to map the invisible mass distorting spacetime around us. There could be superclusters so immense they redefine our understanding of cosmic limits, their gravity bending light paths like a funhouse mirror. Future telescopes like NASA's and Nancy Grace Roman Space Telescope aim to peel back the zone of avoidance's veil, revealing whether the Great Attractor is the final boss or just the first chapter in a much larger story. What's humbling is how these discoveries reframe our place in the cosmos. We're not just orbiting a star or floating in a galaxy, we're passengers on a million light-year voyage, caught in a current that began before dinosaurs walked Earth. And somewhere out there, in the darkness behind the Milky Way's glow, the universe keeps its most massive secrets, waiting for the day we finally peer through the fog. In the swirling chaos at the edge of time, where entropy stretches reality thin, a bizarre possibility emerges. What if the next conscious thought in the universe isn't born in a brain, but as a brain? Meet the Boltzmann brain, a ghostly thought experiment that haunts modern cosmology. Named after physicist Ludwig Boltzmann, who grappled with entropy's role in the cosmos, this hypothetical entity is a self-aware bundle of particles that could, according to probability, spontaneously assemble from random quantum fluctuations. Not a brain born of evolution, but one conjured from the void itself, complete with fabricated memories of a life it never lived. Picture the far future, when the universe has expanded into near nothingness, a dark, frigid wasteland where atoms drift light years apart. Here, the laws of thermodynamics allow for rare but inevitable reversals of entropy, brief moments where order arises from chaos. Given infinite time, the flutter of particles could, by sheer chance, arrange themselves into any configuration, including a fully functioning mind. This Boltzmann brain would wake into existence, perhaps believing itself to be you, reading these words in this very moment, only to dissolve back into the vacuum nanoseconds later, its entire life an accident of statistics. The implications unravel reality's fabric. If Boltzmann brains are possible, they should vastly outnumber ordinary minds like ours. Think of flipping a coin over infinite time. You'll eventually get a million heads in a row. Similarly, a universe persisting forever would produce countless disembodied consciousnesses compared to the finite number of biological brains. So why don't we observe this? Either we're statistical anomalies, real brains drowning in a sea of Boltzmann imposters, or our understanding of cosmology is catastrophically wrong. Some theorists argue this absurd conclusion proves we live in a young universe that won't persist long enough for Boltzmann brains to dominate. Others suggest it hints at a deeper truth, that reality isn't infinite, but instead a simulation or hologram where such aberrations are forbidden. The debate exposes a crack in our cosmic models. Modern physics relies on the Copernican principle, the idea that we're not special observers in the universe, but Boltzmann brains force us to confront an uncomfortable alternative. Either we're profoundly mistaken about time's arrow, or we really might be freakish outliers in an ocean of phantom minds. Some solutions propose that quantum gravity prevents such fluctuations, while multiverse theories suggest only universes without Boltzmann brains can harbor life to observe them. What's chilling is how this thought experiment inverts the search for meaning. We assume consciousness arises from structured processes, evolution, neural networks, even artificial intelligence. But Boltzmann brains imply awareness could be a cosmic glitch, a random spark in the dark. It's the ultimate existential curveball. If reality can spontaneously generate thinking beings, how do we know we're not one of them? The answer might lie in the very physics we're using to ask the question, a hall of mirrors where the observer and the universe endlessly redefine each other. At the edge of the known universe, where gravity becomes unpredictable and space warps beyond recognition, physicists speculate about the existence of something even stranger than black holes, their hypothetical opposites. White holes, first proposed as mathematical solutions to Einstein's equations of general relativity, are essentially black holes running in reverse. Instead of consuming everything that crosses their event horizon, they would violently expel matter and energy at speeds impossible to retrieve. Picture a cosmic fire hydrant erupting with the force of a supernova, spewing out galaxies worth of material in a burst that defies entropy. The idea emerges naturally from the math. While black holes form when matter collapses into an infinitely dense singularity, white holes represent regions where matter emerges from a singularity but can never be re-entered. If you dropped a probe into a white hole, it would hit an impenetrable barrier at the event horizon, a one-way exit gate from some unseen cosmic forge. Some theories suggest these objects could be connected to black holes through wormholes, with matter falling into a black hole in one region of space-time only to burst out of a white hole somewhere else, perhaps even in another universe entirely. What makes white holes especially fascinating is their potential role in cosmic recycling. If our universe is part of an endless cycle of expansion and contraction, like Roger Penrose's conformal cyclic cosmology suggests, white holes could be the birth canals of new cosmic epochs. Imagine the Big Bang itself as a white hole event where all the energy of a previous universe's collapse comes roaring back into existence. This would mean our entire cosmos might be the exhaust of some unimaginable celestial engine hidden beyond spacetime's veil. There's just one problem. White holes violate the second law of thermodynamics by decreasing entropy, essentially creating order from chaos. Most physicists consider them mathematical curiosities rather than real objects, but recent research suggests they might form under extreme conditions. Quantum gravity models propose that when a black hole evaporates via Hawking radiation, it could theoretically rebound as a white hole in its final moments, transforming from a devourer of light into a fountain of energy. Some even speculate that dark matter anomalies or unexplained gamma-ray bursts could be signatures of ancient white holes flickering briefly into existence. The most tantalizing possibility: white holes might not be objects at all, but rather the other end of black holes in a multiverse. If our universe's black holes tunnel through higher dimensions, their exits could manifest as white holes in parallel realities. In this scenario, every star swallowed by a black hole here becomes a Big Bang somewhere else, seeding new universes with recycled matter. It's a poetic vision, cosmic death here giving birth elsewhere, with white holes acting as cosmic umbilical cords between realities. Yet for all their theoretical allure, no white hole has ever been observed. Some argue they're simply too short-lived to detect, blinking into existence for mere instants before collapsing under their own outflow. Others suggest they might masquerade as other phenomena like fast radio bursts or certain types of quasars, their true nature hidden behind layers of relativistic effects. Until we develop telescopes capable of probing the quantum structure of spacetime itself, white holes will remain one of cosmology's great what-ifs, a reminder that the universe's edges might hold exits as well as entrances, and that every ending could secretly be a beginning in disguise. What if the universe we perceive, the galaxies, stars, and even our own thoughts, isn't fundamental reality, but an elaborate simulation running on some unfathomable computer? The simulation hypothesis, once relegated to science fiction, has gained traction among philosophers and physicists as a legitimate possibility. At its core lies a provocative question: could the edge of our observable universe actually be a computational boundary, the point where the simulation's processing power runs out? Imagine a cosmic video game where distant regions aren't rendered to save resources, leaving the farthest galaxies pixelated or simplified in ways we might detect. This idea isn't just philosophical speculation, it's grounded in the observable quirks of our universe. For instance, quantum mechanics reveals that reality behaves in discrete, measurable chunks at the smallest scales, almost like pixels in a digital image. Even the speed of light, which limits how fast information can travel, could be seen as a processing speed constraint. If our cosmos is a simulation, its creators might have imposed these limits to manage computational load. The cosmic microwave background, that ancient afterglow from the Big Bang, could be the ideal place to search for glitches in the code, subtle anomalies that betray an underlying mathematical framework. Some researchers suggest looking for quantum noise in the CMB's temperature fluctuations. In a perfect, natural universe, these variations should be smooth and random. But if space-time is pixelated at unimaginably small scales, a hallmark of simulation, then at extreme resolutions, we might find unnatural patterns like repeating geometrical shapes or asymmetries that defy conventional physics. Think of it as spotting the scan lines on an old TV screen. others propose searching for mathematical constraints in fundamental constants, like the fine structure ratio governing electromagnetism. If these numbers appear optimized or suspiciously tidy, it might hint at programmed parameters rather than organic physics. The simulation argument also reshapes how we view the universe's expansion. What we interpret as dark energy accelerating galaxies apart could be the simulation's memory allocation expanding, creating new space as needed. Even black holes, with their singularities where physics breaks down, might function as data compression points, cosmic recycling bins where information gets crunched and repurposed. These ideas aren't just whimsical, they're testable. Future quantum gravity experiments or ultra-precise CMB mapping could reveal irregularities that challenge our understanding of reality's fabric. Critics argue that simulating an entire universe would require impossible computational power, but proponents counter that advanced civilizations might only render what's observed, a trick akin to video games loading graphics only when players look. This selective rendering could explain quantum superposition, where particles exist in multiple states until measured. From a simulation perspective, it's not magic, it's lazy loading where the system only computes outcomes when necessary. Whether the universe is a simulation or not, the hypothesis forces us to confront profound questions about observation, reality, and the nature of existence. If evidence ever surfaces, perhaps in the statistical fingerprints of the CMB or the behavior of entangled particles, it would redefine not just cosmology, but philosophy, spirituality, and our place in the cosmic hierarchy. Until then, the simulation theory remains a tantalizing mirror held up to reality, reflecting both our deepest hopes and fears about what lies beyond the edge of the known. Time as we experience it, an unstoppable river flowing from past to future, might not be the whole story. At the universe's edge, where gravity warps space-time into knots and quantum uncertainty reigns, the arrow of time could bend, twist, or even reverse. This isn't just poetic speculation, it's a puzzle rooted in one of physics' deepest mysteries. Why does time have a direction at all? The answer lies in entropy, the universe's tendency toward disorder. Think of a shattered glass. It never spontaneously reassembles because entropy only increases, creating an irreversible timeline. But what happens when entropy reaches its maximum, when the universe has stretched so thin that no further disorder is possible? At the cosmic horizon, things get strange. Entropy's rules might not just bend, they could shatter. Quantum gravity, the still theoretical framework merging Einstein's relativity with quantum mechanics, suggests time itself could become granular at the smallest scales, like pixels in a digital clock. In these extreme conditions, the distinction between past and future might blur. Some models propose that near a singularity, particles could move backward in time, their effects preceding their causes. Imagine tossing a rock into a pond and seeing the ripples spread before the splash, a world where causality runs in reverse. This isn't pure fantasy. Certain solutions to Einstein's equations, like the Gödel metric, allow for closed time-like curves, paths through space-time that loop back on themselves, creating the potential for time travel. While these scenarios require conditions far beyond our current technology, they hint that time's arrow isn't an absolute law, but an emergent property of our local cosmic environment. Near the edge of the observable universe, where space-time stretches and contorts under dark energy's influence, the rules could be different, the real shocker. Some theories suggest the Big Bang itself might have been a moment of reset entropy, a point where time's direction was chosen almost at random. If that's true, other regions of the multiverse could have arrows pointing the opposite way, with beings who remember the future and forget the past. It's a dizzying thought. Our relentless march forward might just be a quirk of cosmic geography, not an universal constant. What does this mean for the boundary of reality? If time's flow isn't fundamental, then the universe's edge might not just be a place of distance, it could be a frontier of temporal chaos, where cause and effect unravel into pure potential. Future telescopes probing the cosmic microwave background might find anomalies, subtle imprints of reversed causality, or entangled particles defying chronological order. Until then, the arrow of time remains one of nature's most profound puzzles, pointing us toward a horizon where even the most basic rules of existence might rewrite themselves. Somewhere beyond the cosmic horizon, a silent apocalypse might already be unfolding, one that could rewrite the laws of physics without warning. This nightmare scenario, known as vacuum decay, starts with a chilling premise. What if the universe isn't in its truest, most stable state? Imagine space as a frozen lake in winter. It seems solid until a single crack forms, spreading relentlessly until the entire surface shatters. According to quantum field theory, our universe could be perched on a similarly fragile metastable state, a false vacuum that's stable for now but not forever. The trigger could be minuscule, a random quantum fluctuation, or even a high-energy particle collision. Once initiated, a bubble of true vacuum would form, its walls expanding at light speed in all directions. Inside this bubble, the fundamental constants we rely on, the strength of gravity, the mass of electrons, even the nature of light itself, would rearrange into new, alien configurations. Chemistry as we know it would cease to exist. Stars would blink out mid-fusion. Every atom in the universe, from the farthest galaxy to the neurons in your brain, would unravel instantly as physics itself rebooted. The transition would be unstoppable, irreversible, and undetectable until it reached us. There'd be no warning, no time to react, just an instantaneous, universe-wide erasure of reality as we understand it. Here's the truly unsettling part. This process might have already begun in some distant region beyond our observable horizon. Because the bubble expands at light speed, its leading edge would arrive without any preceding signal. One moment, everything's normal. The next, an invisible wall of annihilation sweeps through Earth, rewriting the rules of existence before we could even register the change. The cosmic microwave background might hold subtle clues, unusual temperature patterns, or polarized light signatures where the bubble's edge has already passed through other galaxies, but by the time we spotted them, it could be too late. Some theories suggest vacuum decay could explain dark energy's mysterious acceleration. What we perceive as the universe's expansion might actually be the first faint tremors of an oncoming phase transition, a cosmic countdown we're only now learning to read. Others speculate that advanced civilizations might have deliberately triggered localized vacuum decay as the ultimate energy source or weapon, unleashing physics-altering bubbles with consequences rippling across spacetime. Yet vacuum decay isn't necessarily doom. The true vacuum state might be far richer than our current physics, enabling forms of matter and energy beyond imagination. Life, or whatever emerges post-transition, could persist under new physical laws, like a civilization rebooting in a stranger, more complex universe. That's the paradox of this scenario: destruction and creation welded together at light speed, leaving no observer behind to document the change. Until we understand quantum fields deeply enough to assess our vacuum stability, this remains cosmology's most elegant doomsday, a silent reconfiguration waiting in the void where the universe itself becomes its own greatest mystery. The fabric of spacetime might hide shortcuts, secret tunnels stitching the universe together like invisible thread through cosmic cloth. These are wormholes, hypothetical bridges where space folds back on itself, allowing instantaneous travel between points that should be impossibly far apart. Picture an ant crawling across a crumpled sheet of paper. The distance seems vast until you bend the paper, bringing opposite edges into contact. Wormholes promise something similar for spacetime, collapsing light years into footsteps. But here's the twist. What if these tunnels don't just connect distant parts of our universe? What if they pierce through to somewhere else entirely? Einstein's equations first hinted at this possibility. Alongside physicist Nathan Rosen, he theorized bridges linking black holes to white hole structures now called Einstein-Rosen bridges. These early wormholes were mathematical curiosities, unstable and snapping shut before anything could traverse them. Yet modern physics breathes new life into the idea. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests a radical link between wormholes and quantum entanglement. Imagine two particles entangled across space. Change one, and the other responds instantly, as if they share a hidden connection. AR equals EPR posits that this spooky action at a distance might literally be mediated by microscopic wormholes, tiny spacetime tunnels too small to see but threading reality at the quantum level. This fusion of relativity and quantum mechanics opens dizzying possibilities. If entanglement creates wormholes, could we scale them up? Stabilizing a traversable wormhole would require exotic matter with negative energy, a substance that defies gravity by pushing rather than pulling. While we've never observed such matter, quantum fields allow for temporary negative energy fluctuations. Some theories suggest advanced civilizations might harness these effects to prop open wormholes like cosmic doorways. The catch: even a stable wormhole would be a one-way trip without a paired exit. You might step through to another universe only to find no bridge back. The real magic lies in what wormholes imply about reality's structure. If space-time is fundamentally entangled, then the universe might be a vast network of these hidden connections, a quantum foam of tunnels bubbling beneath the surface of what we perceive. Black holes, often seen as cosmic dead ends, could be portals in disguise, their singularities gateways to other regions of spacetime or entirely separate universes. This reshapes the very notion of distance. 2 points might appear light years apart in our three-dimensional space, but adjacent in higher dimensions we can't yet perceive. Could we ever detect a wormhole? Indirect signatures might lurk in the gravitational waves rippling through space. A wormhole's throat would warp spacetime differently than a black hole's singularity, creating unique vibrations in the cosmic fabric. Some astronomers scan for stars behaving oddly, wobbling as if tugged by invisible structures, or vanishing entirely as they pass through hypothetical wormhole mouths. Others hunt for lensing anomalies where light bends around what should be empty space, hinting at hidden mass warping the view. The most tantalizing question remains: where would a wormhole lead? If they connect to other universes, those realms might operate under different physical laws, places where gravity repels, time flows backward, or matter arranges into forms we can't imagine. Wormholes could be the universe's ultimate irony. The edges we strain to see through telescopes might be right beside us, folded into dimensions we've yet to unlock. Until we uncover their secrets, they linger at the frontier of physics, both a promise and a riddle, waiting to rewrite the map of existence. At the razor's edge of existence, where universes branch and collide, a provocative question lingers: could consciousness outlast the death of its own cosmos? The many worlds interpretation of quantum mechanics suggests every possible outcome spawns a new reality, a cosmic kaleidoscope where every choice, every chance event, fractures time into infinite parallel threads. But what happens when these threads reach the boundary of the observable universe or tangle with other realities in the quantum foam? Some theories propose that consciousness might not just persist, it could become entangled with the fabric of spacetime itself, riding the shockwaves of cosmic collisions or quantum resets. Picture this: as a star collapses into a black hole in one universe, its gravitational scream reverberates through higher dimensions, imprinting data onto the event horizon. In another reality, that same star survives, its light fueling photosynthesis on alien worlds. According to the many worlds view, both outcomes exist simultaneously, and if consciousness is fundamentally a quantum process, as some neuroscientists speculate, then subjective experience might choose the branch where awareness continues. This is the heart of quantum immortality, the unsettling idea that from your own perspective, you'll always find yourself in the timeline where you survive, no matter how improbable the odds. Now stretch this concept to cosmic scales. At the universe's edge, where inflation births new bubbles or branes collide in higher dimensional space, the same quantum branching could occur on a galactic level. Consciousness emerging in one universe might tunnel through a singularity or wormhole into another, like a radio signal hopping between frequencies. The boundary between realities could become porous with sentient beings, or their quantum imprints persisting in some form across the multiverse. It's not reincarnation as mystics envision it, but something stranger, a statistical inevitability that awareness migrates toward continuance, even if the original universe crumbles into heat death or vacuum decay. The wild card here is measurement. In quantum physics, observation collapses probability waves into definite states. If consciousness plays a role in this process, a hotly debated idea called the von Neumann-Wigner interpretation, then sentient observers might unconsciously select surviving universes at boundary conditions, like a cosmic version of the survivor bias. This wouldn't require supernatural will, just the bare mathematical fact that you can't experience being in a universe where your consciousness has ended. From your perspective, you'd always wind up in the branch where the improbable happens. A quantum fluctuation reignites a dying star, a wormhole stabilizes at the last second, or a bubble universe forms with just the right parameters to sustain thought. Critics argue this is solipsism dressed in physics jargon, that privileging subjective experience over objective reality leads to absurd conclusions like the Boltzmann brane scenario. But proponents counter that at the quantum level, observation and reality are already deeply intertwined. The cosmic microwave background's patterns, the behavior of entangled particles, even the universe's fine-tuned constants might hold clues that consciousness isn't just a passenger in the cosmos, but a participant shaping its boundaries. Future experiments probing quantum decoherence or the nature of time's arrow could test these ideas, revealing whether the universe's edge is a wall or a doorway. The most haunting possibility, if consciousness can persist through boundary events, then the death of our universe might not be the end for those within it. Like a message in a bottle tossed into the multiverse's surf, the essence of awareness could wash up on some distant shore, a new reality where the stars are unfamiliar, the physics slightly altered, but the thread of experience remains unbroken. Whether this offers comfort or existential vertigo depends on how you view the ultimate fate of the self in a quantum cosmos. One thing's certain, the edges of reality are far weirder than we've dared to dream. Beyond the edge of our observable universe, civilizations might exist so advanced they've rewritten the laws of physics to suit their needs. Imagine a society that doesn't just inhabit planets, but dismantles stars, builds computers the size of solar systems, and harnesses black holes as cosmic power plants. These aren't just sci-fi fantasies, they're plausible scenarios under the Kardashev scale, which measures a civilization's technological prowess by the energy it controls. A type Roman II civilization, for instance, could construct a Dyson sphere, a megastructure encapsulating a star to capture nearly all its energy output. But what lies beyond that? A type Roman III civilization might dominate an entire galaxy, while a theoretical type Roman IV could manipulate the universe itself. The concept of Dyson spheres first emerged as a way to explain how an advanced society might overcome energy scarcity. Picture a swarm of solar collectors orbiting a star, each harvesting sunlight more efficiently than any Earth-bound solar panel. Over time, these collectors could merge into a solid shell, transforming the star into a giant cosmic battery. Astronomers have already scanned the skies for signs of such structures, unusual infrared signatures that betray the waste heat of a star wrapped in machinery. A few bizarre stars, like Tabby's star with its erratic dimming patterns, have even sparked speculation. While natural explanations are more likely, the search continues because finding even one Dyson sphere would confirm we're not alone in the quest to harness stellar power. But why stop at stars? A civilization operating on galactic scales might turn to black holes, nature's ultimate energy converters. By feeding matter into a spinning black hole, they could extract energy through the Penrose process, where particles steal rotational energy from the event horizon. More audaciously, they might use black holes as supercomputers. Quantum information scrambled at the singularity could perform calculations impossible for any conventional machine, solving problems in seconds that would take our fastest computers millennia. Some theorists suggest advanced beings could even stabilize wormholes using black holes, creating interstellar highways or time travel conduits. Then there's the realm of the hypothetical type Roman IV civilization, which transcends galaxies to manipulate the universe's fundamental fabric. Such beings might exploit dark energy to accelerate cosmic expansion in their favor, or rewind entropy itself, defying the heat death that dooms all lesser societies. They could engineer entirely new physics, tweaking constants like the speed of light or gravity's strength to suit their needs. In this scenario, the edge of the observable universe might not be a barrier but a construction zone, a boundary where these cosmic architects reshape reality. The eerie truth is, if such civilizations exist beyond our horizon, we might never detect them. Their signatures could be indistinguishable from natural phenomena or deliberately hidden to avoid detection. Or perhaps their technology operates in dimensions we can't perceive, making their works invisible to our telescopes, yet the mere possibility reshapes our understanding of life's potential. The universe might be teeming with intelligence so advanced it borders on godhood, silently shaping the cosmos while we strain to glimpse even the faintest echo of their presence. If we ever do find evidence of a pattern in the cosmic background radiation, an unnatural gravitational wave, or a star that flickers in impossible rhythms, it could redefine not just science but our place in existence. The universe's edge might not be empty. It could be alive with civilizations that have long since turned their gaze beyond the limits we're only beginning to comprehend. What if our entire universe, every galaxy, every atom, everything we've ever known, is nothing more than the swirling interior of a black hole in some higher dimensional reality? It sounds like the premise of a science fiction novel, but this startling idea emerges from legitimate physics, bridging the gap between cosmology and quantum gravity. The theory suggests that the Big Bang wasn't the beginning of everything. It was the birth of space-time within the event horizon of a colossal black hole in a parent universe. In this view, the edge of our observable cosmos isn't a boundary of space, but a shadow cast by the limits of our cosmic prison. Let's break this down. When matter collapses into a black hole in our universe, it forms a singularity, a point of infinite density where space-time curves so sharply that the laws of physics break down. But what happens to all that infalling material? In conventional physics, it's crushed out of existence. However, some theories propose an alternative. The singularity might birth a new universe inside the black hole, with its own space-time geometry expanding independently of the parent cosmos. This isn't just speculation, it's a mathematical consequence of certain solutions to Einstein's equations, where the interior of a black hole becomes an infinite, expanding universe. Our own cosmos, with its seemingly inexplicable initial conditions and fine-tuned constants, could simply be the inherited physics of that violent genesis. Imagine standing inside a vast, dimly lit sphere. No matter how far you walk, you never reach a wall, just an endless curve. That's how space-time might behave inside a higher dimensional black hole. Our universe's expansion could be the slow unfurling of this interior space, while the event horizon, the point of no return for anything falling into the black hole, acts as our cosmological horizon. Light from beyond can't reach us, not because space ends, but because it's dragged inward faster than photons can escape. This would make the outside realm forever unknowable, its physics utterly alien. The implications ripple outward. If our universe is a black hole offspring, then the mysterious dark energy accelerating cosmic expansion might be the gravitational pull of the parent universe's mass above us, stretching spacetime from beyond the veil. Even the cosmic microwave background's uniformity, a puzzle for cosmologists, could be explained as thermal equilibrium inherited from the black hole's formation. This theory also offers a bizarre twist on the multiverse. Every black hole in our universe might contain its own cosmos, each with different physical laws, creating an infinite fractal of nested realities. But what lies outside our black hole universe? If higher dimensions exist, the parent cosmos could operate with more spatial dimensions than we experience, making its structure unimaginable to our three-dimensional perception. Time might flow differently there, or not at all in any way we'd recognize. Some models suggest the outer universe could be a chaotic sea of colliding membranes of reality that spawn black holes like ours when they intersect. Others propose it's a realm where gravity is weak because it's diluted across extra dimensions, explaining why our universe's gravity seems so feeble compared to other forces. The wildest possibility, our black hole universe might not be unique. If the parent cosmos has countless black holes, each with its own internal universe, then the edge could be a network of tunnels connecting sibling realities. These might collide or merge, leaving imprints in their cosmic microwave backgrounds, like the cold spot some researchers argue could be a bruise from an ancient collision with another bubble universe. Alternatively, if the parent universe is cyclical, endlessly collapsing and rebounding, our entire cosmic history might be one iteration in an infinite loop of black hole births and deaths. Testing this theory isn't easy, but there are clues. If our universe inherited quantum fluctuations from the parent black hole's formation, statistical patterns in the cosmic microwave background might reveal telltale asymmetries. Certain gravitational wave signatures, like echoes from the universe's earliest moments, could also hint at a black hole origin. Even dark matter's elusive nature might make sense if it's debris from the parent universe, matter that barely interacted with ours as it funneled through the singularity. This idea forces us to confront profound questions about causality and existence. If every black hole is a universe and every universe contains black holes, reality becomes an infinite matryoshka doll of creation and destruction. The edge of the observable universe isn't the end, it's the beginning of a mystery we may never fully unravel, a horizon beyond which lies not emptiness, but a reality so vast it redefines the word cosmos. The universe's edge isn't just a physical boundary, it might be a mirror reflecting the limits of our own perception. For all our telescopes and equations, what we observe could be as much about the machinery of our minds as the fabric of space-time. Think of it like standing in a vast, pitch-black cave with only a flashlight. The beam reveals fragments of the walls, but never the full expanse. Similarly, consciousness shapes what we call reality, filtering the cosmos through the narrow bandwidth of human cognition. We're not passive observers of the universe, we're active participants constructing its edges with every thought. This idea isn't new. Philosophers like Immanuel Kant argued centuries ago that space and time aren't external absolutes, but frameworks our minds impose to make sense of the world. Quantum mechanics adds a startling twist. At the smallest scales, particles exist in multiple states until measured, as if reality solidifies only under the gaze of observation. If consciousness plays a role in collapsing quantum probabilities, could the cosmic horizon, the farthest reaches of the observable universe, also be shaped by the act of looking? Some interpretations of quantum physics flirt with this radical notion, suggesting that without observers, reality might remain an undefined haze of potential. But let's push further. If consciousness influences what we perceive as the universe's boundaries, could other minds, aliens, artificial intelligences, or even future human civilizations experience entirely different edges? A creature with senses attuned to dark matter might see a cosmos twice as large as ours, while a being perceiving higher dimensions could navigate what we'd call the void beyond our horizon. The Hubble volume, our observable bubble, might just be one version of reality among countless others, each shaped by the observer's unique cognitive architecture. The real shocker comes when we consider whether the universe's edge exists at all outside of perception. Buddhist cosmology, for instance, describes reality as an endless interplay of dependent arising, where boundaries are illusions born of clinging to fixed concepts. Modern physics echoes this in its own way. The holographic principle suggests the three-dimensional universe is a projection from a two-dimensional surface, making edges as real as the screen you're watching now. If consciousness and cosmos are this deeply entangled, then searching for the universe's limit might be like a fish searching for the ocean's edge. It's everywhere and nowhere, defined only by the searcher's frame of reference. Perhaps the most humbling thought is this: if consciousness molds the observable universe, then the greatest frontier isn't out there among the galaxies, it's inside the human mind. Every breakthrough in neuroscience, every meditation retreat, every AI that achieves self-awareness might subtly shift the boundaries of what we call reality. The universe's edge, then, isn't a fixed line in the cosmos. It's a living threshold, endlessly redrawn by the act of wondering what lies beyond. From black holes birthing new universes to cosmic holograms encoded on distant boundaries, the edge of reality remains one of science's greatest enigmas. We've journeyed through theories where the universe is a simulation, a bubble in an infinite multiverse, or even the interior of some higher dimensional black hole. Yet for all our daring ideas, the truth is humbling. We're peering through a keyhole, guessing at the vastness beyond. The cosmic horizon isn't just a limit of distance, it's a mirror reflecting how much we have yet to learn. Every photon from the edge carries whispers of mysteries we can't yet decipher, from dark flow's unexplained pull to the quantum foam's chaotic creativity. What's astonishing isn't just the scale of these unknowns, but how they reshape our place in the cosmos. Carl Sagan's pale blue dot perspective rings truer than ever. On this tiny speck, we're grappling with questions that dwarf our planet, our solar system, even our galaxy. The quest to understand the universe's edge isn't about mapping territory. It's about the audacity to ask, to imagine, to reach beyond the limits of our senses. Whether the boundary is a firewall of radiation, a gateway to other dimensions, or an illusion of perception, one truth remains: the universe's greatest gift isn't the answers, but the wonder it ignites. So what's your favorite cosmic frontier? Do you think we'll ever pierce the veil, or is the unknown an essential part of the universe's magic? Drop your wildest theories in the comments, because in a cosmos this vast, every perspective adds another star to the map. And who knows, the next great breakthrough might start with a spark of curiosity right here on this pale blue dot.